Hello and welcome to the first week of Applied Accelerated Artificial Intelligence course. So as we know from the syllabus, in this week we will cover the AI system hardware and accelerators. So it will be divided into 5 segments. In the first segment we will talk about the CPU architecture and what is necessary to understand from the performance point of view to model the high performance AI workloads to run with high efficiency. In the segment 2 we will go towards the memory, because the data, which is the essential ingredient of any AI workload, will be covered or stored into the memory, so where your data stays, and how this entire memory hierarchy will be essential for you to understand to design high performance AI workload deployment. That we will discuss in the segment 2 overview. And in the segment 3 we will talk about GPUs and accelerators, mostly design specific accelerators like TPUs and vendors from let's say Google, you have AMD, you have NVIDIA. So from NVIDIA we have GPU, from Google we have tensor processing units. So we will talk about the GPU and accelerators for the AI workload deployment. And in the segment 4 we will talk about the interconnects. Interconnects are very important in this AI deployment scenario, because nowadays you will see lots of high performance interconnects are available. So what do they mean, and also what performance they can bring into your AI workload, that also we will see in this segment 4. In the segment 5 we will talk about the entire software stack. What exactly goes from starting from your, maybe you write Python import and your library, so starting from there till the silicon, each layer, where does it map and how it actually enhance the performances. So that we will talk about from the software stack point of view in this segment 5. As we talked about in the previous slide, we will talk about CPU architecture and AI workloads. So workloads means we will define few parameters, metrics in this week. Those things will be used throughout your course, so that is essential to understand. So understanding how CPUs are structured, why AI demands more than the general purpose processing unit that you have in laptops, in desktops, in your mobile phones, and even workstations and server PCs. So those aspects we will discuss in this segment. In the end, we will cover the key microarchitectural concept, which will be from the modern CPU perspective. So what is the pipeline, the cache, the ALU, how it is involved in the AI workload deployment, and essentially how these performances are extracted through several levels of parallelism, like instruction level parallelism, like you have data level parallelism, and so on and so forth. So all these things we will discuss, and also we will discuss what are the differentiating features of the performance category in CPU and GPU. So what exactly makes them separate and how they are, obviously each individual has its role in the AI workload deployments. So we will understand their performance point of view. So CPUs are mostly latency optimized and GPUs are designed to be throughput optimized. So all these aspects we will discuss, and what exactly the GPUs are good for what the CPUs are good for, we will do a kind of study in this segment. Also we will identify the flops, which is one performance metric, the memory bandwidth, the cache capacity, as well as some other critical parameters for AI metric or AI workload deployment, and also performance analysis. So how we will say that this deployment is better than the previous deployment, and so on and so forth. So we are talking about acceleration, accelerating the AI workloads. So we need to understand what are the metrics that will be used to define this acceleration point of view, right? And also we will analyze the bottleneck in the entire system, computing system. So after we understand the entire computing system, we will be able to analyze the von Neumann bottleneck, essentially that is lying in the memory, main memory. So that we will discuss, and also the impact on the DNN inference. And also subsequently we will go towards the training and how it is optimized and all these different acceleration technologies or methods that we will discuss. So coming into the microarchitecture for the CPUs, when you write a simple line of code, let's say x equal to a plus b in the Python, that transforms into several sets of or sequence of instructions which are supposed to be executed in the pipeline of the CPU, right? So this is an overview of the microarchitecture of the CPU. We will not go into the deep details, that is not necessary at this stage, but we will discuss what exactly are the bottlenecks. So pipeline means these instructions are executed in the CPU microarchitectural pipeline. So typically the modern CPUs are having 5-stage pipelines, as you are seeing here. Instruction fetch, decode, execute, then memory access, then the write back. So when we are talking about these instructions are getting executed in the pipelines, that means they are executed in several stages, right? So in the instruction fetch stage, the instructions are being fetched from the memory. Then the instruction decode stage will see what exactly this instruction means, and then in the execute stage the actual operation will happen. In the memory access stage, the memory will be accessed either to read data or to write data, and then in the write back register or write back stage, we will write the result into the register of the CPU. So these are the 5 stages which are typical in the modern CPUs you are seeing. Okay. So to improve the performance, what we do superscaling. That means this data path that you are seeing, that is copied or that is replicated into several execution engines, and we execute or we pipeline the executions as well as the instructions that are coming in. So essentially you are seeing here the multiple such instruction fetch, decode, execution, memory and write back is happening, and these are happening into several such execution engines, and that is the superscalar way of doing things. So all the modern processors are basically superscalar engine. So there are no scalar engine which is doing only the single pipeline, rather they are doing a lot of pipeline. That means there will be 4 to 6 instructions issued at the same time, and they will be executed or gone through these pipeline stages subsequently. The modern processors also have this mechanism called out of order execution. Out of order execution means that is for the instruction level parallelism. What we do, if some stalls happen, let's say some instruction is waiting for data to be collected from the memory, that time let's say there is no dependency in the subsequent instructions. Let's say instruction 4 was getting executed and instruction 4 is waiting for the data to come from the memory. That time, if the instruction 5, which is the next instruction supposed to get executed, is ready to be executed, it will be executed. So that means the order of execution is no longer sequential, but rather based on the dependencies we can execute out of order fashion. So this is the out of order execution that actually enhances the instruction level parallelism and also the performance of the CPU. In addition to all these sophisticated techniques, we have also the branch predictors, which reduces the pipeline stalls on conditional branches. So when one instruction is getting executed, there will be prediction units which are seeing which branch to take, let's say if there are any branches there in the next or subsequent instructions. So that's how the core components work in a very sophisticated way, highly sophisticated way. When your one instruction is getting executed, there will be several out of order buffer that will be basically ready for execution, and also there will be predication units which are working tirelessly to see which conditional branches to be taken. At the same time, there will be operating system running. So essentially all these things are happening inside the CPU, and that's why CPU is very sophisticated, and we have core as the pipeline superscalar out of order and branch prediction. Here in this slide you are seeing one such example of the CPU microarchitecture of Xeon processor, Intel Xeon processor. And here we are seeing the different levels of caches that are present in the modern CPUs. So usually 3 levels of caches are present. Here you are seeing the L1 cache, which is highly integrated inside the core, that is tightly coupled with the core itself. There is L2 memory, which is L2 level of cache or level 2 cache, and there is this L3 cache which is shared among these different cores that are available. Okay. And we have different sizes, like in this Xeon example you are seeing L1 is 32 KB per core, we have L2 which is 256 KB per core, we have L3 which is 3260 MB per core, shared because this is shared among these different cores. And you have obviously this DRAM, which is your dynamic RAM, which is the main memory, which is of course in capacities of GBs or gigabytes, right? Now the distance between the core and this cache hierarchy defines the latency or the access time of the memory, because the data will come from the different levels of memory, right? So the core pipeline that is running this instruction, which is basically taking the data is coming from L1, which is very short distance, which is 4 cycles away. L2 is 12 cycles away, 12 cycles latency. L3 around 40 cycles latency, which is bit far from L2, but highly close from the DRAM, which is around more than 200 cycles latency, and essentially your memory wall presents inside this DRAM that we will discuss later. And that actually defines the bottleneck running of AI workloads in the modern CPUs and systems. In this slide we are seeing the different CPU specifications from the AI context or AI workload point of view, because we need to understand what exactly the performance achievable from these CPUs, and that will be given by the specification as you are seeing here, like AMD EPIC processor, which is 9654 series here, has 96 cores and 384 megabytes of L3 cache, and 12 channel DDR5 memory that we will talk about later. You will understand what exactly it is and how it improves the performance of this entire system. Intel Xeon Max 9480, which has around 60 cores, and you can see this HBM2E on package is there inside this Intel Xeon Max core. And also this 9654 EPIC AMD version achieves around peak performance of teraflops of 4 to 6 teraflops. So when we talk about teraflops or gigaflops or Gflops or Tflops, here flops means floating point operations. So floating point operations means if my data type is floating point 32, how much maximum performance that I will get out of this system, which is 4 to 6 teraflops, versus if you take one state of the art GPU which is having around 1000 teraflops. So you can see the difference between the peak performance of the CPU and GPU here. So that means these many operations can be executed in the CPU. So you have to keep in mind always the pipeline, different stages, the out of order execution, the superscalarness of the core, as well as branch prediction. Everything is going on at the same time, and you are getting 4 to 6 teraflops per second. So that means teraflops performance into the peak performance of floating point operations for the AMD core that you are seeing here. Obviously our commodity hardwares or commodity CPUs, these are workstation grade or server grade CPUs. You will have lesser performance in the normal CPUs used in laptops and desktops. The bandwidth, which is another very important metric while designing the AI workload, need to be kept in mind, which is the memory bandwidth, where we get for the CPU DDR5 we get around 300 gigabytes per second, versus if we have H100 GPU with HBM3, we have around 3.35 terabytes per second. So what this bandwidth means, that we will talk about later. So these are few specifications that we keep into mind while designing this AI workload. So essentially the key insight is that CPUs are very good at serial branch type of workloads, latency sensitive workloads. For AI training and inference, which are basically massively parallel matrix multiplications, we will talk about different AI workloads in the subsequent interactions as well, but usually they are highly large or high dimensional matrix multiplications which are used in both AI training and inference in modern AI workloads or algorithms, which are not good to be run directly onto the CPUs with this performance of 4 to 6 teraflops performance, peak performance, right? So how we can improve the performance of the CPUs? So there are different parallelism that we can extract, like instruction level parallelism, the data level parallelism, and so on and so forth. So instruction level parallelism are extracted by using the superscalar, because we know if we can issue 4 to 6 instructions per cycle, that means I will have, or I will increase the number of instructions that it is getting executed per unit time, right? So that is the superscalar unit. And also out of order execution, as we said, that if the instruction is stalled for memory access or some other dependency reasons, then also we can improve the instruction level parallelism by checking the next set of instructions, are they ready to be executed or not. So that means we can execute more instructions parallelly. So that's the out of order window. So usually what the modern CPU does is that modern CPUs have this buffer called the reorder buffer. So reorder buffer looks ahead around 200 to 250 instructions in advance and see which instructions are dependent and which instructions we can execute early, even if the stalls happen in the previous instructions. So that means this window gives us to look ahead around 200 to 250 instructions, which is limited, but this gives an opportunity to extract instruction level parallelism. Obviously there are data hazards and also control hazards which limits this instruction level parallelism. As I said, data stalls is one reason for which we will not get exactly or ideal superscalar performance or out of order performance because of the dependencies and hazards, like data hazards like raw, WAR, the read after write, write after read, write after write, different hazards are there, and control hazards which caps the effectivity or effectiveness of the instruction level parallelism extracted by these mechanisms of superscalar and out of order window. So to improve further performance, what these modern processors do, they improve the data level parallelism on the same time. So SIMD is one such extension that is added to the processors, like we have AVX 512 extension in the AMD processors. In the Intel processors we have AMX extension. So SIMD extensions are usually called, what is the SIMD? Single instruction multiple data. So from the name itself we know or we understand that this is to extract the data level parallelism. So single instruction operating on multiple such data. So the AVX extension operates on 16 such data, floating point 32 per cycle, and operates in vector processor register, which is 512-bit registers they operate on. Similarly, the Intel has added this AMX extension to tile or to do matrix multiplication on the matrix tiles up to 1024 bytes. Okay, so that accelerates the on chip the matrix multiplication as well as vector operations, like to be done on, let's say, 16 such floating point of data at the same instruction or same time we can do that. So SSE is another such instruction which is operating on 4 floating point 32 data per cycle, which was introduced in earlier versions of Pentium processors, but modern day processors has this two extensions in AMD and Intel versions. Okay, but does this bridge the gap of doing thousands or millions of parallel data operations to be done for these matrix multiplications for AI workloads? Not really, because there is a parallelism gap. For an example, a ResNet 50 inference will need around 4 billion, the multiply and accumulate, 4 billion MAC operations to be done for the inference. So you can imagine these many of operations if we have to do with faster processing, 16 floating point 32 or even 1024 bytes of data to be processed at single cycle will not cut the execution time. So like for an example, 96 core EPIC processor with AVX 512 extension that we saw here will give you around maximum 12 teraflops operation peak performance, whereas your NVIDIA H100, which is Hopper architecture, the state of the art NVIDIA architecture, which will give you around 2000 teraflops, which is operating on TF32. Okay, so these, this gap we will not be able to bridge by only this extension of SIMD or the instruction level parallelism, right? So for training LLMs, CPU only is 100 times, 1000 times slower than the GPU based systems, and that's why we need to see what exactly the GPUs are good for and what exactly the CPUs are good for. So that's why the Roofline model is very important. The Roofline model for GPUs and CPUs you are seeing here, the dotted line represents the Roofline model for the CPU EPIC 9654 system and GPU H100 that you are seeing here. Okay, so obviously the x-axis represents here the arithmetic intensity, which is the performance and the memory bandwidth ratio. That means how much performance or how many operations that we are doing per the data or per byte of data that we are loading from the memory. Okay, so that is the arithmetic intensity, and y-axis represents here the attainable performance, which is gigaflops per second or gigaflops. So again, this you can talk in terms of throughput as well. So throughput is number of operations performed per unit time. So here you can see this performance per unit time, which is basically your gigaflops per second or gigaflops, and here x-axis you are seeing the arithmetic intensity. Now arithmetic intensity is a function of the workload itself or the kernel itself or the applications that we are trying to run, right? Because number of operations that we will do per memory byte that we are loading or we are getting from the memory, that depends on the application. And here on the y-axis, the attainable performance, peak performance we will get from the hardware, right? So this gives you an idea about where your workload resides, right? So here this is the peak performance curve, and here is the peak memory bandwidth curve, which is the slope that you are seeing here, and this straight line is essentially your peak performance, and where it collides, this intersection point decides which workloads are essentially your memory bound workload, which is the left hand side of this intersection, and on the right hand side we will get the workloads for compute intensive, right? So we talked about this parallelism gap, right? So 4 billion multiply and accumulate operations that we have to do, right? So if we talk about in terms of workload, you can see that the transformer attention, which is the very large dimension matrix multiplication operation that we can do for transformer models, which resides here. So that is way above the compute performance, maximum compute performance that we can get from the CPU itself, right? And this depends, or this lies into this the memory bound workload of this GPU, right? So what does that mean, and what exactly that refers to while designing or coding for those models or deployments into the system, that we have to understand basically. And reach is compute bound. You can see that is almost towards the intersection point, right? And other workloads like linear normalization, batch normalization, which are highly memory bound for the CPU, as well as you can see here, embedding lookup, right? So these are different workloads for or different parts or steps of your AI workloads, which are running inside the different bound here for the CPU and GPU. Okay. So arithmetic intensity we talked about, this is ratio of flops and memory traffic for your large matrix multiplication, which is around, let's say, 1000 flop per byte. So that means per byte that we are loading the data from the memory, we have to do 1000 flop. So that means this is basically your compute bound on GPU, okay, compute bound application or compute bound kernel for your system. The embedding lookup, on the other hand, we have one flop, one floating point operation per byte. So you load 1 byte of data and you do one floating point operation. So this is your memory bound, okay. So you do not do many operations for your loaded data. So that is your memory bound, right. Similarly, batch normalization, linear normalization. So as you can see, these are essentially this arithmetic intensity or function of the application itself, the kernel. So from the AI workload, you can understand what exactly, whether this is compute bound or memory bound, right. And similarly, batch normalization, linear normalization, these are memory bound. You do around 3 to 5 flop operation, floating point operation per byte data that you download, right. So now we talk about the von Neumann bottleneck. So data resides in the memory, right, DRAM. So here is your DRAM, which is 200 cycles plus cycles away. And here we have both the data and instruction, right. So you have the von Neumann architecture here. So single shared bus between the CPU and memory. The main memory here we are talking about. Obviously in the cache you have the segregation between the data and instruction, but essentially your data and instruction coming from the data DRAM. So memory access is serialized and compute units starve for while they are waiting or computing the data. So if you see the trend of improving the compute performance of the systems, you see a growth of around 1.5 times, 2 times even gain in the processor speed till maybe 2002, 2005. So from 2005 it hit the memory wall. So essentially you can no longer wait, or the memory is basically you cannot increase the clock speed and you hit the memory wall as well as the power wall, because if you increase the clock frequency beyond this 3.5 or 3.12 gigahertz, so essentially you will melt the chip itself. So CPU clock speed grew 60% around per year till 2002. Now it's plateaued. And the DRAM bandwidth grew around 10% per year. So DRAM bandwidth is not essentially growing at the same speed of your compute speed. So that means there is a gap which is brewing, and in 2005 we saw the maximum gap between this memory bandwidth and the compute. So that means compute are getting faster, but data is not coming fast. So you just wait for the data to arrive to get computed, right. So modern DRAM latency is around 60 nanoseconds, plus if you consider the cache miss penalty, which is 200 plus cycles. So basically you are hit by the memory wall, which is because your data is residing here in the DRAM, right, which is far away from your compute unit in the CPU, right. So in terms of AI workloads, if we talk about the impact, the transformer attention, let's say it's matrix multiplication, right. So order of n square memory that we need to access. So the access pattern is order of n square space that we need to access. So for LLM inference, we need to have millions of operations to be done based on the token that we download. So it's memory bound. So DNN training are compute bound. So large mini batches fill arithmetic units, right. So that means we are basically bound by the memory wall. For an example here, 70 billion parameters are there in a model. For, let's say, imagine it that we are trying to train for a model, okay. So we have 70 billion parameter in the model of FP16 data type, floating point 16 bits. That is around 140 gigabytes of data. So it should be loaded at every cycle or every single token generation step, right? Because for an LLM, so this is a LLM token generation example where we are doing or generating single token for this particular LLM model, which is 70 billion parameters. So for every single token, I have to take into account 70 billion parameters of the model. That is 140 gigabytes of data. So you can imagine, right? At 400 gigabytes per second bandwidth. So if I have a memory bandwidth of 400 gigabytes per second, so that will take around maybe 350 milliseconds per token, right? And that is just the memory bandwidth. Okay, so compute can be in minutes. So this is, let's say, training we are doing, right? So for this LLM training, I have this token to be generated, and that is where we have to load 140 gigabytes of data. And at 400 gigabytes per second bandwidth, we take around 350 milliseconds per token to be get processed. So that is just the bottleneck that we are facing. And if it is your computing is in minutes, then it is fine. If it is seconds, that means you have to wait to get the data and then to compute, right? So CPUs in the AI pipeline are not that obsolete also, because for pre-processing, post-processing, CPUs are very crucial, because you have these data ingestion, the tokenization, augmentation, branchy type kernel execution, right? Like if you have to have OpenCV and working on images, videos, so you have to decode, you have to augment the data. So all these things are to be done by the CPU, right? So data shuffling, batching, all these processes will be done by the CPU, which are very good at. It may not be good at billions of matrix multiplication operation to be done, but it is good at this pre-processing, post-processing, the model components that remain on CPU, which are also like sparse operations. So we will talk about many such applications, like let's say in reinforcement learning, you have dynamic graphs which are sparse in nature. You need to have CPU's intervention to effectively compute them. Control flow in reinforcement learning, step reset, very good at CPU. Okay, runtime on CPU, NNX runtime. So this also we'll talk about later. Variable lightweight models in production that are very good at CPUs, which are server grade CPUs obviously. And that's where this heterogeneous computing comes in. In GPU, we are very good at doing matrix multiplication, GEM, right? General matrix multiplication, MAC operations, right? Thousands, millions of billions of parallel such operations. But CPUs are good at orchestration, control flow, the serial computation, right? Data augmentation, IO management, and so on. So that's why this heterogeneous computing is very essential in AI workloads. And always profile before overloading or offloading the data, and this also we'll talk about in subsequent lectures. And what are the key metrics we should look at, and where to look at, and how to exactly all this heterogeneous computing to be managed into this AI workload deployment. We'll discuss this. So with this, I will summarize this segment, which is CPUs are deep in pipelines, caches, the out of order execution, the SIMD latency. SIMD is for latency optimized serial computation, and memory wall essentially constrain the CPU performance for data heavy tasks, because AI are data heavy tasks. And also the SIMD extension partially closes the gap between the data to be processed and the instructions, but that does not match the GPU scale parallelism, right? Arithmetic intensity is very important for AI workload, so you should learn how to compute this looking at a particular workload. So it's very easy. Again, the ratio between the operations and the bandwidth or the memory operations. And the CPUs remain essential for the data preprocessing, orchestration, control flow, or control heavy tasks in the AI pipelines. So with this, we will conclude this segment. Thank you.